Hi everyone, I am Anis Fatima from 2nd MSc Mathematics. Today we have to see how to solve one linear programming problem by using bounded variable algorithm. First we have to see what is the algorithm. Step 1 is, if the LPP is of minimization type, convert it into maximization type, which means we have one linear programming problem with objective function, constraints and non-negative restrictions. Suppose we have the objective function is of minimization type, then we convert it into maximization type. Step 2. If right hand side of any constraint is negative, make it positive by multiplying the constraint by -1. The step 3 is, convert the LPP to standard form by adding slack and surplus variable and applying the initial basic feasible solution, which means we have the constraint which is either less than or equal to type or greater than or equal to type. Suppose the constraint is less than or equal to type, then we add slack variable. Otherwise, if the constraint is greater than or equal to type, then we add surplus variable. Step 4. If any of the variable is at positive lower bound, which means the non-negative restriction has any lower bound, then substitute it out as it is lower bound by Lj equal to xj minus xj dash or xj equal to Lj plus xj dash, where this xj is greater than or equal to 0. Step 5 is, first compute the net evaluation Zj minus Cj and examine their sign. If all Zj minus Cj is greater than or equal to 0, then we have the current basic feasible solution as optimum 1. If at least one Zj minus Cj is less than 0, then the current basic feasible solution is not optimal. Then we move on to the next step. Step 6. Choose the most negative Zj minus Cj. Let it be some Zr minus Zr for some j equal to r. The corresponding non-basic variable xr is now entered into the basis. Step 7. Compute the quantities theta 1 equal to minimum of xbi by air, where air is greater than 0. Theta 2 equal to minimum of ui minus xbi by minus air, this air is less than 0. And ur is the upper bound of entering variable xr. And next we have to find the theta value, which is the minimum of theta 1, theta 2 and ur. It is to be noted that if all the air is greater than 0, then theta 2 equal to infinity. In this step, we have three cases. The first case is, if theta equal to theta 2, which corresponds to xbk, then the xk leaves the basis. This xk being non-basic at its upper bound must be substituted by xbk or equal to xbk or dash minus akr into u, where this xbk or dash is in between 0 and ur. And xbk denotes the variable xr at upper bound is put at 0 level by using xr equal to ur minus xr dash, where 0 less than or equal to xr dash less than or equal to ur. Next case 2, if theta equal to theta 1, which corresponds to xbk, then this xk leaves the basis, then we use the regular operation of simplex method. Next case 3, if theta equal to ur, then xr is substituted as its upper bound while remaining the non-basic, that is, it can be put at 0 level by using xr equal to ur minus xr dash. Step 8, go to step y and repeat the procedures until an optimum basic feasible solution is obtained or there is an indicator of an unbounded solution. This is the bounded variable algorithm. Now we have to see one example. Solve the following LPP model by the upper bound algorithm, that is, which means bounded variable algorithm. The LPP is maximize z equal to 3x1 plus 5y plus 2x3 subject to the constraints x1 plus y plus 2x3 less than or equal to 14, 2x1 plus 4y plus 3x3 less than or equal to 43. The non-negative restrictions are 0 less than or equal to x1 less than or equal to 4, 7 less than or equal to y less than or equal to 10, 0 less than or equal to x3 less than or equal to 3. In these constraints, we have the second constraint as 7 less than or equal to y less than or equal to 10. So first we have to change this non-negative restriction as y equal to x2 minus 7. Now the standard LPP is maximize z equal to 3x1 plus 5. In terms of y, we have to substitute x2 minus 7 plus 2x3. In this LPP, the constraints are less than or equal to type. So we have to add slack variable as x4 and x5. So the maximization z will be 3x1 plus 5 into x2 minus 7 plus 2x3 plus 0x4 plus 0x5. Maximize z which implies maximize z equal to minus 3x1 minus 5x2 minus 2x3 plus 0x4 plus 0x5, which equal to 35, which means plus into minus 7 equal to minus 35, which is equal to 35. Subject to the constraints x1 plus in terms of y we have to substitute x2 minus 7 plus 2x3 plus x4 equal to 14. Next, x1 plus x2 plus 2x3 plus x4 equal to 7, which change into x1 plus x2 plus 2x3 plus x4 equal to 7. In this equation, the x4 is the slack variable. Next constraint, 2x1 plus 4 into, in terms of y we have to substitute x2 minus 7 plus 3x3 plus x5 equal to 43, which changed into 2x1 plus 4x2 plus 3x3 plus x5 equal to 15. Now, the non-negative restrictions are 0 less than or equal to x1 less than or equal to 4. The second one is y, which can be changed into x2. Therefore, the non-negative restriction is changed into 0 less than or equal to x2 less than or equal to 3. And another one is 0 less than or equal to x3 less than or equal to 3. Now we move into the algorithm. First, starting table. So the headings are basis, x1, x2, x3. This x4 and x5 are slack variables, and solution ratio. So we have the objective function as maximization z. So z. The slack variables are x4 and x5, which forms x4 and x5. The z value as minus 3, minus 5, minus 2, 0, 0. The solution is 35. And x4 values are 1, 1, 2, 1, 0. The solution is 7. x5 values are 2, 4, 3, 0, 1. The solution is 15. So in this table, the most negative value is minus 5, which corresponds to x2. So x2 enter the basis. Now we have to find the three values theta 1, theta 2 and u2. Theta 1 is minimum of the ratio values. So first we have to find the ratio for x4 and x5. The ratio for x4 is solution divided by the x2 value. So 7 by 1. And the ratio for x5 is solution divided by the x2 value, 15 by 4. So theta 1 equal to minimum of this 7 by 1 and 15 by 4 equal to 15 by 4 is a minimum value, which corresponds to x5. Now theta 2. In the column of x2, all the values are positive other than z value. So we have to take theta value as infinity, which means since all the values in x2 is positive except z value. Next we have to find u2. u2 is the upper bound of x2. We have the non-negative restriction as upper bound of x2 is 3. So u2 equal to 3, which is the upper bound of x2. Now we have to find theta, which is the minimum of theta 1, theta 2, u2, which is equal to minimum of 15 by 4, infinity and 3. In these values, the minimum is 3, which corresponds to u2. So using the algorithm, the minimum value is u2. So we make substitution as x2 equal to 3 minus x2 dash. This 3 is the upper bound of x2. So now the LPP is changed into maximize z minus 3x1 minus 5 into, in terms of x2 we have to substitute 3 minus x2 dash. Therefore minus 5 into 3 minus x2 dash minus 2x3 equal to 35, which implies maximize z minus 3x1 plus 5x2 dash minus 2x3 equal to 35 plus 15 is 50. Subject to the constraints x1 plus 3 minus x2 dash plus 2x3 plus x4 equal to 7, which implies x1 minus x2 dash plus 2x3 plus x4 equal to 7. This plus 3 is changed into minus 3. So 7 minus 3 is 4. Next constraint 2x1 plus 4 into, in terms of x2 we have to substitute 3 minus x2 dash plus 3x3 plus x5 equal to 15, which implies 2x1 minus 4x2 dash plus 3x3 plus x5 equal to 15 minus 12 equal to 3. The non-negative restrictions are 0 less than or equal to x1 less than or equal to 4, 0 less than or equal to x2 less than or equal to 3, 0 less than or equal to x3 less than or equal to 3. Now we have to change the previous table by changing the values of this LPP. So the first iteration table is basis x1. We have to change the x2 variable as 3 minus x2 dash. So the variable is x2 dash, x3, x4, x5, solution ratio. So z, here the slack variables are x4 and x5. The z values are changed into minus 3, 5, minus 2, 0, 0, 50. This value corresponds to the previous maximization z values. And the x4 value is 1, minus 1, 2, 1, 0. The solution is 4. x5 values is 2, minus 4, 3, 0, 1. The solution is 3. Here also we have to repeat the same procedure. We have to find the theta 1, theta 2 and u1. Theta 1 is minimum of the ratios. So first we have to find the ratio for x4 and x5. The ratio of x4 is the solution divided by the pivotal column value. So 4 divided by 1, and the ratio for x5 is the solution divided by the pivotal column value. So 3 by 2. Theta 1 is minimum of 4 by 1 comma 3 by 2, which is equal to 3 by 2, which corresponds to the variable x5. Here also theta 2 equal to infinity, because all the values in the x1 column is positive except z value. Now we have to find u1, because x1 is enter the basis and x1 has the most negative value. So we have to find u1, which is equal to 4, which is the upper bound of x1. Now we have to find the theta value, which is the minimum of theta 1, theta 2, u2, which is equal to minimum of 3 by 2, infinity and 4, which is equal to 3 by 2, which corresponds to the value theta 1. So in the case of theta 1, by using the algorithm, we have to make the next step as we use simplex method. So x5 leaves the basis. So first we change the pivotal element 2 as 1 by dividing this row by 2. So first, next we change the remaining 2 rows by using the formula old value minus the pivotal element into new value. So first I enter the previous elements minus 3, 5, minus 2, 0, 0, 50. The pivotal element is minus 3. So formula is minus. So minus into minus plus 3 into this 1 is new value. So 3 into 1 equal to 0. 5 plus 3 into minus 2 equal to minus 1. Similarly, we have to calculate these column values. Similarly, here the old values are 1, minus 1, 2, 1, 0, 4. Here the pivotal element is 1. So formula in formula minus, so minus 1, minus 1. Here the 1, minus 2 are new values. So calculate this, we have these values. So second iteration table, now we change the first iteration table into the second iteration table by changing these values. So basis, the values are x1, x2 dash, x3, x4, x5. These are variables. Here the variables are z, x4, x1. Now the z value is changed into 0, minus 1, 5 by 2, 0, 3 by 2. The solution is 109 by 2. Next x4 column is changed into 0, 1, 1 by 2, 1, minus 1 by 2, 5 by 2. x1 values changed into 1, minus 2, 3 by 2, 0, 1 by 2, 3 by 2. Here we also repeat the same procedure. Here the most negative value is minus 1. So x2 dash is enter the basis. Now we have to find the theta 1, theta 2 and u2. Because x2 dash is the most negative value, so we have to find the corresponding u2. First theta 1 is minimum of ratio values. Here the ratio is exists only x4 value, because x1 value has a ratio as negative value, so we neglect these terms. So theta 1 equal to minimum of the ratio of x4 is 5 by 2, which is equal to 5 by 2, which corresponds to x4. Next theta 2 equal to, in this table, x2 dash has one negative value which corresponds to x1. So here we have to find the theta 2 value. Theta 2 equal to upper bound of x1. Upper bound of x1 is 4 minus the solution of x1 is 3 by 2. So 4 minus 3 by 2 divided by the pivotal element is 2. So divided by minus of minus 2, which is equal to, which is 2. So theta 2 equal to 4 minus 3 by 2 by 2, which corresponds to x1. Next, here x2 dash has the most negative value. So we have to find u2 value. The upper bound of u2 is 3. Now we have to find theta equal to minimum of theta 1 comma theta 2 comma u2, which is equal to minimum of 5 by 2 comma 5 by 4 comma 3, which is equal to 5 by 4, which corresponds to theta 2. So now we follow the algorithm. In case of theta 2, we make substitution as x1 equal to 4 minus x1 dash, because theta 2 is 5 by 4, which value is correspond to x1. So we make substitution as x1 equal to upper bound of x1 is 4 minus x1 dash. Now the previous LPP is changed into maximize z minus x2 dash plus 5 by 2 x3 plus 3 by 2 x5 equal to 109 by 2. This value of maximize z is taken into the previous second iteration table. Subject to the constraints x2 dash plus x3 by 2 plus x4 minus x5 by 2 equal to 5 by 2. Next constraint is minus x1 dash minus 2x2 plus 3 by 2 x3 plus 1 by 2 x5 equal to minus 5 by 2. The non-negative restrictions are same. So third iteration table, we have to change these values into third iteration table. So the table headings are basic, x1 dash, x2 dash, x3, x4, x5 solution ratio. Here the basic variables are z, x4. In terms of x5, we have to change this as x1. So here the most negative value is minus 1, which corresponds to x2 dash. So x2 dash enters the basis. First we have to calculate theta 1 equal to minimum of the ratio of x4 and x1. So first we have to find the ratio of x4 and x1. x4 ratio is 5 by 2, x1 ratio is 5 by 4. So theta 1 equal to minimum of 5 by 2, 5 by 4 is 5 by 4, which corresponds to x1. Next we find theta 2 equal to, here also in x2 dash column, we have one negative value which corresponds to x1. So we have to find theta 2 value. Theta 2 equal to upper bound of x1 4. Here the solution is minus 5 by 2. So minus into minus plus. So plus 5 by 2 divided by, here the pivotal element is minus 2. So divided by minus of minus 2 is plus 2. So theta 2 equal to 4 plus 5 by 2 by 2, which corresponds to x1. u2 equal to 3, which is the upper bound of x2 dash. Now we have to find theta equal to minimum of theta 1, theta 2, u2, which value is 5 by 4, which corresponds to theta 1. So in the case of theta 1, by algorithm, we use simply the simplex method. So here x1 leaves the basis. So first we change the pivotal element minus 2 as 1 by dividing the whole row by minus 2. Next we change the remaining 2 rows by using the formula old value minus pivotal element into new value. So similarly we have to calculate these values and substitute the table. We have the fourth iteration table as z value as 1 by 2, 0, 7 by 4, 0, 5 by 4. The solution is 223 by 4. And x4 value as minus 1 by 2, 0, 5 by 4, 1 by minus 1 by 4. And the solution value is 5 by 4. x1 value as 1 by 2, 1, minus 3 by 4, 0, minus 1 by 4, 5 by 4. In this table, we have all the Zj minus Ej values are positive. So we obtain the optimum solution. So we stop the algorithm procedure here. The optimum solution is x1 dash. In this table, x1 equal to 5 by 4, but we have x1 dash equal to 0. We make substitution as x1 equal to 4 minus x1 dash. Here x1 dash value is 0, so x1 value is 4. x2 dash equal to 5 by 4. We make substitution as x2 equal to 3 minus x2 dash. In terms of x2 dash, now we substitute 5 by 4. So x2 value is 7 by 4 and x3 value is 0. We make substitution as y equal to x2 minus 7. So y equal to x2 value is 7 by 4 plus 7 equal to 35 by 4. So we have maximize z equal to 12 plus 175 by 4 equal to 223 by 4, which is the optimum solution of this problem by using bounded variable algorithm.
Hi everyone, I am S. Sivasri from 2nd MSc Mathematics, V. Vaniya Perumal College for Women, Virudhunagar. Here, the maximized z is equal to 4x1 plus 2x3 plus 6x3 subject to 4x1 plus x2 less than or equal to 9 minus x1 plus x2 plus 2x3 less than or equal to 8 minus 3x1 plus x2 plus 4x3 less than or equal to 2. The non-negative restrictions are 0 less than or equal to x1 less than or equal to 3, 0 less than or equal to x2 less than or equal to 5, 0 less than or equal to x3 less than or equal to 2. Now we can convert the standard form. The maximized z is equal to 4x1 plus 2x3 plus 6x3 plus, here the constraints are less than or equal to type. We can add the slack variables 0x4 plus 0x5 plus 0x6 subject to 4x1 plus x2 plus x4 equal to 9 minus x1 plus x2 plus 2x3 plus x5 equal to 8 minus 3y1 plus x2 plus 4x3 plus x6 equal to 12. The non-negative constraints are 0 less than or equal to x1 less than or equal to 3, 0 less than or equal to x2 less than or equal to 5, 0 less than or equal to x3 less than or equal to 2. Here the non-negative restrictions slack variables are greater than or equal to 0, x4, x5, x6 greater than or equal to 0. An initial basic feasible solution for slack variables are x4 is equal to 9, x5 is equal to 8, x6 equal to 12. The upper bound of the slack variables is infinity. Let us start by using the starting table. Here the tables are basis x1, x2, x3, x4, x5, x6 solution ratio. we can put the z as 1. We can convert the given LPP into maximize z minus 4x1 minus 2x2 minus 6x3 minus 0x4 minus 0x5 minus 0x6 subject to 4x1 plus x2 plus x4 is equal to 9 minus x1 plus x2 plus 2x3 plus x5 is equal to 8 minus 3x1 plus x2 plus 4x3 plus x6 equal to 12. We can use the table by using these values. We can get the most negative value is x3. Hence the x3 enters the basis. Now we can find the theta 1 by using the formula theta 1 is equal to minimum of ratio values 8 by 2, 12 by 4. The 8 by 2 comes from solution divided by variable entering the basis. 8 by 2 is equal to 4, 12 by 4 is equal to 3. Minimum which is equal to theta 1 is equal to minimum of 4, 3 is equal to 3, which is corresponding to the value x6. Here all AR is greater than or equal to 0, and theta 2 is equal to infinity. U3 is equal to 2. U3 means x3 upper bound is 2. Apana U3 is equal to 2. Theta is equal to minimum of theta 1, theta 2, U2 is equal to, which is a minimum, we get 2. 2 is corresponding to U3. We can make substitution by using x3 is equal to 2 minus x3 dash. Here 2 is the upper bound of U3. Now we can convert the maximization problem into maximize z minus 4x1 in the place of x3. Maximize z minus 4x1 minus 2x2 minus 6 into x3. In the place of x3 we can substitute 2 minus x3 dash plus 0x4 plus 0x5 plus 0x is equal to 0. Subject to 4x1 plus x2 plus x4 is equal to 9 minus x1 plus x3 plus 2x3 in the place of 2 into 2 minus x3 dash plus x5 is equal to 8 minus 3x1 plus x2 plus 4 into x3. We can substitute 4 into 2 minus x3 dash plus x6 equal to 12. 0 less than or equal to x1 less than or equal to 3. 0 less than or equal to x2 less than or equal to 5. 0 less than or equal to 2 minus x3 dash less than or equal to 2. All slack variables are greater than or equal to 0. Therefore, maximize z minus 4x1 minus 2x3 plus 6x3 dash plus 0x4 plus 0x5 plus 0x6 equal to 12. Subject to 4x1 plus x2 plus x4 is equal to 9 minus x1 plus x2 minus 2x3 dash plus x5 is equal to 4 minus 3x1 plus x2 minus 4x3 dash plus x6 equal to 4. 0 less than or equal to x1 is less than or equal to 3. 0 less than or equal to x2 less than or equal to 5. 0 less than or equal to 2 minus x3 dash less than or equal to 2. All slack variables are greater than or equal to 0. We put these values into the table. Basis x1, x2, x3 dash, x4, x5 solution ratio. Is that x4, x5, x6? We can use the table. We can find the least value as most negative value as x minus 4, which is in the column of x1. Therefore, x1 enters the basis. Now we can calculate theta 1 equal to minimum of solution divided by pivotal column. 9 divided by 4 is equal to 9 by 4, which is a ratio. Here x5 and x6 has the negative value which cannot be calculated for the ratio value. Minimum of 9 by 4 is equal to 9 by 4 corresponding to the variable x4. Here all ARs are greater than or equal to 0, which is theta 2 is equal to infinity. And u3 is equal to 3, which is the upper bound of x1. Theta is equal to minimum of theta 1, theta 2, u are equal to 9 by 4, which is equal to theta 1. We can use the simplex method. Here x4 leaves the basis. We can divide the x4 column divided by 4. We can convert the first iteration into by dividing the x4th row by divided by 4. 4 by 4 is equal to 1, 1 by 4 is equal to 1 by 4, 0, 1 by 4, 0, 0, 9 by 4 we get. For other values, we can calculate the formula using the old value minus new value into pivotal element. Here, minus 4 is, z has minus 4, minus of pivotal element is minus 4 into new value is 1 equal to 0. We can calculate in the similar manner, we get the values of z. In the similar manner, we can calculate x1 and x6 for also. Here theta 1 is equal to minimum of 9, 5, 43 by 7, which is equal to 5, which is corresponding to x5. And theta 2 is equal to infinity. u2 is the upper bound of 2 is equal to 5. Therefore, theta is equal to minimum of theta 1, theta 2, ur. This is equal to 5, which is equal to theta 1. Here you can use the simplex method. Therefore, we get x5 leaves the basis and x2 enters the basis. 4 by 5 divided by 5 by 4 x5 row. Hence x5 leaves the basis and x2 enters the basis. Divide x5 row by 5 by 4. We get 0, 1, minus 8 by 5, 1 by 5, 4 by 5, 0, 5. For the other values, we can use the formula old value minus pivotal element into new value. We get the another values. Here all Zj minus Cj are greater than or equal to 0. Hence the solution is optimum. Therefore, x1 is equal to 1, x2 is equal to 5 and x3 dash is equal to 0. We can use the substitution x3 is equal to 2 minus x3 dash is equal to 2. Therefore, x1 is equal to 1, x2 is equal to 5, x3 is equal to 2. Therefore, maximize z is equal to 4 into 1 plus 2 into 5 plus 6 into 2 is equal to 26. Hence the solution. Thank you.